Welcome. I'm Stefan Franssen. I'm a postdoc. I'm currently at the Sorbonne. At 1st October, I'll start at Oxford as a postdoc. I will be talking about my research in the Bernstein-von Mises theorem for semiparametric mixture models. But I will first start with the historical development, and my own research comes completely in the end. If there are any questions, I can derive most things here on the blackboard. I can explain things. We can keep this low key and just ask many questions. If you want to see the more technical details, I also have appendices at the end of my slides with more technical parts of my proof. But we'll just keep it easygoing, not too deep, not too hard. So what are semiparametric mixture models? So a mixture model is a model where you have some latent variable that you do not observe. Let's call that Z. And a semiparametric mixture models is basically the idea. We have some parametric model that we want to estimate, but we do not get to observe all the random variables. There's some latent variable Z, and that we can, if we would observe this, we would have a complete parametric model. So that would give us the kernel here, p theta, and then we have the random variable, density given Z. And this is sort of the idea, but we do not get to observe Z, so we model this as an IID sample from some distribution. We call that F, and we're actually not too much interested in this F. We're interested in this parameter of this parametric model, this theta. That is what we want to estimate. So these models can be quite versatile. They can be used to model various things. And that was supposed to be much later on my own research. So one of the examples is the frailty model. So this is a model that's used, for example, in medical research. We have pairs of patients, or example, which is much more a toy example, is we have pairs of light bulbs, and each of these pairs, they are the same type of light bulb, but we do not know its, for example, life expectancy. And then we have some coating that we claim that improves its life expectancy. So of each of these pairs, we will treat one of them with the coating, and we will treat the other one without doing anything. So that gives us two pairs, and they have different distributions. And we will model them as having exponential rate of failure with two different rates, lambda and theta lambda. And what we want to estimate is this theta. And a very naive idea could be to look at, okay, we look at the ratio of the life expectancies of the treated and untreated, and then just take the average of that. That would be sort of your first naive guess, but you can actually write down better estimators by using that these batches of light bulbs, they have some more better control. And the average is sort of a worst case analysis, where you assume that these ratios, they behave in the worst way possible. Another option is to have errors in variables. So we want to do a linear regression of y, that's our parameter of interest, random variable of interest, and we want to have some x of covariates, but we do not get to observe this x exactly. We only observe them with some Gaussian noise. So these are the two main models that I will apply my research to. And then there's also a model that actually my methods, the Bayesian methods, we don't know yet if it will be efficient estimators, but it is from a historical perspective an important one, because we used it to give counterexamples to other methods. Did I now upload? for example, the Nijman-Scott problem. So what people have done before is they just take all these mu i's as parameters and try to do a maximum likelihood estimator, and then the maximum likelihood estimator converges to a half sigma or 2 sigma squared. So I've wrote down a half sigma squared, but I always interchange if it should be a factor half or a 2. And in several papers, people have argued that, you know, Bayesian methods, they don't fall for this problem. They have 0 issues because then comes some statement along the line, Bayes will not suffer from the same failure as the maximum likelihood estimator, as Bayesian inference is based on probability theory and not statistics, and therefore better. So, of course, there's a paper showing that more or less every model that people similar related model, so where you treat all these mu i's as their own parameters with their own prior, that they will be inconsistent and converge to the wrong answer. So a lot of the folklore in the literature is wrong, people believe that things don't go wrong for mixture models, that you can just treat them by putting IID priors on each of the missing latent variables, but that's just not a thing. It will be inconsistent, and they tend to actually converge to the wrong a half sigma squared. But you can fix it by using very convoluted priors. So here they have a prior that's designed specifically for that model, and sort of a mixture of Gaussian. To prove consistency, you have to look at what's called the non-parametric maximum likelihood estimator. So what we will do is we try to maximize the likelihood, not of the latent variables as parameters, but we try to maximize the likelihood of the distribution that these parameters follow. That is sort of inducing a penalization, and then you can show that under some technical conditions that you can compactify the parameter space, which is a fairly weak assumption because you can do this in the weak topology. Then you can show that this non-parametric maximum likelihood estimator actually is consistent. And this was sort of the first step towards getting good results. We know that we can actually get consistent estimators for these mixture models. Then there's another lemma, which is basically folklore. I have never seen an actual proof of this, but everybody knows it. That who works in semiparametric inference is that, okay, you can just assume that the log likelihoods, they form a Glivenko-Kontali class. That means that they will the averages will converge almost surely to the means uniformly. So then you just use that the only mean zero thing is the truth, and then you will get the consistency of the maximum likelihood estimator. So this is more or less the state of this lemma, the proof. And that is more or less the state of consistency theorems that we have for these semiparametric mixture models. But they are very, very broad because a lot of classes of functions are Glivenko-Kontali classes. And it's very easy to compactify these mixture models. So we know that in a lot of cases we can quite easily write down consistent estimators. But we want to have the best possible estimators. We don't want something that eventually converges to the truth. We want something that converges to the truth as fast as possible. So the idea of the efficiency is that we want to estimate this as fast as possible. And then there's this entire theory of regular estimators. So what you can do is say like, okay, we can of course create something called the Hodges estimator that is better, but it is only better at, let's say, a point, and it comes at the cost of the efficiency for any other point. And then you can do like more complex variations of these things, but it will not do this for like any big set of parameters. So there's these theorems that state that if you want to have an estimator that achieves sort of this best possible efficiency bound, then you cannot write down any estimator which beats that on a, let's say, measure zero set, like on more than a measure zero set of the parameter space. So that's sort of the story behind efficiency. And what we want to show, what we want to derive is that we can achieve these efficient estimators in these mixture models. And to the best of my knowledge, the first result on like general efficiency type arguments, it was never completely written in the efficiency story, is the partial likelihood methods. So in partial likelihood is the idea that, okay, in special cases we can like modify our likelihood, and it should be a r theta. So we have this p theta that we can factorize in a way such that this latent variable z does not appear in this first factor. And of course, the way it's written right now, we can do this always, because we can just take q to be 1. And then we take r, which should have had a theta, we just take r theta of x given g is p theta x given g, and then we have not achieved anything. But if we can do this for some special factors, maybe we can achieve efficiency. So yeah, that was a typo. The typo, like there should be a theta. Yeah, but like this r theta should be there. So you can always do this straightforward factorization, but that's not a useful one. What we want to find is a useful one. And then in special models, we can find such a useful one. And we can use this q theta, and we replace the likelihood and the maximum likelihood estimation. Like, we just get rid of the r theta part, and we just use q theta, and we run maximum likelihood estimation, like normal parametric maximum likelihood estimation, because there's no latent variable involved anymore. So we don't have to do anything with like the distribution of that parameter. We only have to focus on this theta parameter. And then we can show that these will be like consistent estimators, asymptotically Gaussian, and quite like in the special cases, they can be efficient estimators. So then Bruce, like let's say, wrote down a condition, and this is sort of on the remainder. And this states that suppose this factor can be written so that this r theta satisfies this condition. And this condition is more or less saying that this ft that we define here, that this is a least favorable submodel, for those who know what like these things are, that for estimating this theta parameter in the model. And if this is the case, we call the model locally fully informative. And if the model is locally fully informative, then we can conclude that line expansion plus locally fully informative, the partial likelihood estimator is efficient. So we have achieved the best possible estimation. Yes? Yes.
Before when you wrote down R, it didn't depend upon theta.
Yeah, as I said, that was a typo.
Ah, okay.
But that's the entire point. Like this, with, like if you fix the typo, so the theta dependence should be in R, it's trivial. You need to put something extra. So the extra thing is that you need to be locally fully informative, and then you are efficient. But you can still, sometimes you can write some interesting estimators here, which are not locally fully informative, and they will still be consistent, asymptotically Gaussian, but they will not be efficient, for example. There are examples of this. So if you look in the paper by Bruce Lindsay, there are like a bunch of examples, and in particular, the errors in variable model and the exponential frailty model, they are examples where you can write down consistent, asymptotically Gaussian, but not efficient, like factors. And turns out that you can't actually write an efficient version of this. Like the least favorable submodel is not of this shape. Any other questions? So partial likelihood theory is nice, but then you have to figure out what are these partial likelihoods. You have to like try to construct these least favorable submodels. There's a lot of work. Can we do something that's easier? Can we do something better? And even after you've done all this work, you might not even get like efficient estimators. So Bruce Lindsay continued his research into like these mixture models, and he showed that you can construct efficient scores. So he assumes that we have a complete sufficient statistic t theta for this latent variable z, and then there's some technical conditions, and then you have the sort of parametric, so you take the log likelihoods and then the derivative with respect to theta, you take the conditional expectation of that thing conditioned on the sufficient statistic, and then you can construct a score with this, and then you can show that this is actually the efficient score. And then using this, there's also counterexamples where like there's some conditions that have to be satisfied, and like you can write down like very simple models. For example, the model where the latent variable is always the same value, but this methodology will not work. So it's important, and they might be technical conditions, but it's important that these conditions are verified because easy counterexamples exist. But a lot of things also are not counterexamples. So then, like, we can use this conditional score just to build a Z estimator. So we just try to look at where the score is 0, but like under the empirical mean. And that gives us an efficient estimator under these technical conditions. So that already brings us a bit further. We have a bit of technical conditions, but we have something that for like a whole lot of models allows us to write down these things. Problem is, we have to have this complete sufficient statistic, and we have to be able to write down all these like conditional expectations, and we have to do all these things in advance, and that's not necessarily easy or available for like, if I just give you a model, it's not obvious what to do. There's a lot of work. So in practice, people use like maximum likelihood estimators, and to do that, you have to understand least favorable submodels. So to understand what the efficiency is, the efficiency is basically attained in a least favorable submodel. It's the hardest model that we can create within our semiparametric, hardest parametric model that we can create within our semiparametric model that really determines how easy it is to estimate these parameters that we want to estimate. And there's a lot of tools and tricks that are available, but for the most part, it's tools and tricks, and you have to remain dedicated. You have to do targeted for a particular model inference. I forgot how much I wrote last night extra on these slides, but there's a tool called calculus of scores that you can use, but the problem is that in a lot of situations, you have to sort of be able to invert some operator, and that operator might not be invertible, so that entire process of doing the calculus of scores then fails, and then you have to do something by hand. You have to figure out what to do by hand. And even if it's invertible, it might not be obvious what the inverse is. So you might not be able to write down the inverse yourself. So the Fisher information of a submodel is given by the variance of the score of this submodel. The score is the gradient of the log likelihood. The efficient score is the score of a least favorable submodel. We've said that before. Then you can wonder, what can we do? For the maximum likelihood estimator, we sort of have hopes. We have seen that it's consistent. In parametric models, if the maximum likelihood estimator is consistent, then it's immediately efficient. So you can hope more or less the same thing for the non-parametric maximum likelihood estimator. And there are sort of theorems along the way, but they have technical conditions. So Art has written a bunch of papers. And let me grab a drink for a sec. So he has written a whole bunch of papers on explicitly this problem, trying to estimate using maximum likelihood estimator, and getting efficient estimation. So there's even more papers than this, but basically it turns out that there we need to somehow be able to understand the least favorable submodel very well to prove that all the conditions in the theorems are verified. So Art has some very abstract conditions, but to verify them in practice, we have to reason along an explicit least favorable submodel and use properties of the submodel to verify these conditions. And these conditions are basically verified for 3 examples: the frailty model, errors in variables, and the scale mixture models. And scale mixtures is the idea that, okay, I have symmetric density, and it has some center point, and I want to estimate the center point as efficiently as possible. Mm-hmm.
Does there always exist a least favorable submodel? And if it exists, is it unique?
No and no. So the efficiency story that I've explained so far is sort of a slight simplification, because what we actually take is the infimum over all submodels, and that infimum might not actually be attained. And if it's attained, you can write down many different submodels because it's sort of a property of a derivative, and you can show, you can set up many different solutions to that differential equation because it only is a requirement at a point that the derivative satisfies certain properties. So you can build many different least variable submodels if you have one. So these are basically the three main examples where Art verified these conditions, and then later he also verified them in a separate paper for a sort of missing data model. But the missing data model is sort of you either observe the full data or no data. So it's a very simple case of missing data, and then that is also amendable to like maximum likelihood estimators, but that's sort of the extent of what you can do with maximum likelihood estimator in the literature. There's also profile likelihood, but in a sense, profile likelihood is just like maximum likelihood estimator, because what you do is for every, so instead of maximize finding the theta and the f at once, you first create a profile likelihood, which is for every theta, find the f that maximizes that likelihood, and then you maximize the profile likelihood. So it's a two-step, but in the end, you sort of get to the same points. They are very related, and they have pretty much the same conditions. My own research is on Bayesian inference. So as we have just seen, like way in the beginning when I was talking about consistency, people write down sometimes statements that Bayesian methods, they like perform automatically better. But there are counterexamples. So for example, this paper by Gianluca and Schmidt-Hieber, like Johannes, they have like studied this Nijmans-Scott problem, and they have shown that in a generalization of the Nijmans-Scott problem, you get inconsistency with these sort of more parametric approaches to doing like these mixture models. So what we have to do is to sort of first figure out, can Bayesian models ever be consistent? And the first thing I did was I actually attended the talk of Gianluca, and he gave this example where like these models fail and why they fail. And I was like, but maybe I can write down a consistent estimate, like a consistent model. And then I was like, okay, let's try. And then I got the idea, okay, we want to estimate this distribution. So what is the kind of price that people use in practice to estimate distributions? So we're not interested in estimating density. We do not need any properties of that. We just want to have the distribution. So in practice, people use species sampling models. So for example, the Dirichlet process, that's the next example. And but like species sampling models, they are like a broad class of distributions, and they are sort of discrete. And you have a collection of like these weights and these points, and these theta I, these point masses, they are IID from some distribution G, and these weights, that's just a random probability vector. So some people would call this a proper species sampling model, but like for this presentation, we call this species sampling. And then this is what people use to model like distributions. And there's some important examples in Bayesian inference. For example, the Dirichlet process is one of these examples, and that's sort of one of the cornerstones in like mixture models, and people use this one all the time for creating these mixture models or estimating distributions. So this Dirichlet process is basically I define a partition, and I want to define
the probability that I assign to these partitions, and I say, okay, this is a random variable with a partition K sets, then I take and draw from the display distribution, so that's just like this finite dimensional distribution, the four components and what are the masses that I assign. So I have two parameters, M and G. G is a probability measure, M is a real positive number. So I just take the product M times G of the first up to M times G of the last part of the partition. This gives us a random vector, and it turns out that this, we can then show that this defines a probability distribution that's random, and what is not at all obvious from its definition that it defines a species sampling process. So it's discrete, there's a bunch of other properties, so we have a nice distribution for this W, wave vector, and the locations, these theta i's, they are drawn from this G from this distribution. That is sort of the main example that people use. This is a well understood process, people like to use it, there's a lot of sampling schemes for this, so I first thought let's try this, but turned out that we proved that I didn't need any properties that are specific to the DFlow process. I just needed species sampling, so I would just do that. So the other example that people use a lot in mixture models is so to model the distribution F itself as a mixture. So we say that a random measure F with power 8 is a probability measure G and H a probability measure of N follows this, then it is a finite mixture. This is a very popular choice because then people typically take this H to be, for example, an exponential distribution. And then you get the things that people learn in practice when they don't use DFlow processes. And that's how people typically model these things. And then let's get into the definition of consistency, so you can actually know what we're talking about. So the standard distribution is said to be consistent at theta naught if for every neighborhood around theta naught, we look at the complement of this neighborhood, and we look at what probability the posterior assigns to this neighborhood, and that has to go to 0, and the theta naught probability. And this has to hold every neighborhood U of theta naught. So this again takes the topology into account. With that likelihood divergence, it's sort of you want to have that the log likelihood is positive. And for the likelihood property is said that we look at the places that have a log likelihood, that is at least, so the way this is going on. So then these things have to be epsilon close, and then the probability that we have some densities such that epsilon close has to be positive. So basically every cubic Laplace neighborhood of the truth, there has to be some positive mass. That's what this cubic Laplace property is saying. And so what you actually have to imagine if this does not hold, then there exists some neighborhood which is 0 mass, so we can't hope to be consistent. And there's no hope because we don't put anything that's epsilon close. So this is a very weak requirement to be consistent. Then there's the Schwarz theorem, which is already an old result to show consistency. And that shows that, okay, you have to have some test, and you have to have a cubic Laplace property, and then you can show consistency. This is a classical result, and there's an inference, And then this has various extensions to get contraction rates where you have to refine all these things, you have to be precise how fast these tests decay and stuff, but now it just has to be for every neighborhood you have to have consistent test. That's it. And then we get consistency. So I thought maybe I can just try to create this test. But it turned out to be more efficient to actually look at the proof of Schwarz's theorem and to look at the proof of the proof of Wolfowitz theorem. We just basically more or less paste them together and we get the results that I proved. So under the condition of the proof of Wolfowitz consistency theorem and the proof of Leibniz property, which is sort of the minimum requirement that you need to have to be consistent, then the theory will also be consistent. Same for preventing from tally classes. Again, same idea, we just use the proof of the Schwarz theorem, but instead of using the test, we use that these classes are preventing from tally classes. And that's got consistent estimation. We can look at efficiency. So this is where stuff becomes technical. I will not go too much into the detail, but like the line expansion is more or less, we just take the first few derivatives and we want to have that this has some nice uniform control and a no read around the truth. So we take a perturbation of the likelihood and these for the submodel, we subtract the likelihoods which is not perturbed and then this has to satisfy this kind of table expansion. Uniformly, this is sort of easy. This is what you prove from maximum likelihood estimation all the time. The difficult part is that you have a second condition, the change of measure condition. And so we have these subsets theta and fn, well, sort of glance over where we have to have the uniform control. So we have this weird likelihood, but then perturbed, and then integrated over the power divided by the unperturbed likelihoods. And this ratio has to converge to 1. And this is the hard part, typically. Because we can, if these assumptions are true, we get the Bernstein-von Mises theorem that states that the posterior distribution will be the efficient estimator. They will have all the nice properties, but let's see typically this result here is the really hard result that we have to show. And then, so we can try to figure out some conditions such that this holds. And that's basically the end of my presentation. I will give some abstract conditions and then I will not show the lemma how you use these conditions so that the change of measure condition holds, but that's sort of the main difficulty of the problem. So first we have to assume a specific shape constraint on the leaf of the submodel. So we have to assume that this Ft actually is sort of a change of variables in the parametric model already. And then there's we can I messed up all of my shots. So the first step is to assume that we have the number of clusters. So because there's a mixture model, so we have clustering points and we want to have not too many cluster points. If we have too many cluster points, that induces a bias. So we have to specify a sequence Km that has to be small over the root n, and we want to show that this particular posterior has so like some nice control that the area of these clusters is not too big. Then this looks very similar, but this is sort of assuming like this looks very similar to what we want to prove. But if you see here, it's the perturbed integrated out over the unperturbed integrated out over these restricted sets. Actually, what is going on here is the perturbed integrated out over these restricted sets divided by the perturbed integrated out without the restricted sets. So this is sort of assuming that we have consistency, then we start concentrating on this theta and Fn. So this is not the same at all as this like changing magic condition. This is just saying that also in the perturbed model we are in a sense consistent. And then we assume this shape, and then we have some technical conditions on this phi t and like properties of the model. They're not too important, they're just sort of a log Lipschitz like a log Lipschitz condition. I give like conditions under which you can verify all these things with only these three assumptions. Then we can verify the change of measure condition. That's more or less the questions, but I said one more order. So we can try to look at why this change of measure condition is so hard. Because naively it's just like, okay, we want to show that this goes to 1, so maybe if we look pointwise, if we can show that uniformly for each point this converges to 1. So for each theta and f, uniformly on this theta and f, this converges to 1. Let's try. So we move the integrals. If we take logarithms, however, what do we get? We get exactly the expression for the line expansion. This line expansion, well, but we're not, that converges to some constant that is like not the 0. So we cannot hope to do this sort of pointwise. And the idea is more or less that maybe we can start matching these points in a different way. So if we can find to every theta and f a perturbed version, since that these things actually, so that the ratio, so we don't go like literally pointwise to point, we try to show that for every theta and f there exists a theta prime f prime such that theta prime minus t over square down f prime minus t over r. That's that converges to 1. So maybe we can sort of create a change of variables in a sense. And that's sort of the idea behind all these proofs. So we want to prove that there's some change of variables going on in the background. If we do not assume that's more or less the intuition behind all these proofs. And if we do not assume this, we do not know how to verify this condition. So that's sort of the real difficulty at the moment. And it's almost necessary to have this change of variable condition, but it's so far unclear if you can prove it in any other way. Like we can't prove that assuming the change of measure condition you have a change of variables going on in the background, that it's almost necessary because you don't get any other control on the points. Okay, so that's the sort of the intuition that you want to do. And then you have a whole bunch of assumptions that you need to make such that you can actually write it as sort of changing variables. Any questions? You can go to all these proofs and see which has sort of the best asymptotic, the best approximation to the asymptotic properties, but I mean, for the most part, that's really hard. So there are nice asymptotic properties that allows to give interpretations to like, okay, these credible sets that we use, the typical Bayesian machinery that also has some more objective interpretation. So and then gives it some trust that what we are doing is not dealing as completely astray. So and the asymptotics kick in pretty quickly. So you don't need to have like large, that's a typical critique that, it's just asymptotics. It only happens if you have infinite data. But for a fixed prior, you get quite often quickly in the asymptotic regime. Like the proofs don't really require like giant constants or that's not going on. So like the behavior is quite nice. Doesn't tell us what kind of priors you should use, but builds and the science bars. So is only species sampling models. There's a very broad class of models, and we can look at when are these conditions satisfied. So for that are needed to prove the change in measure condition. And that had one really important condition, namely the number of clusters in the posterior. And that one is telling us something about what should we be looking for here. And the Dirichlet process has this property of these clusters, like finite mixtures, if you assume some exponential tail, has these nice properties, but some other examples, the Pitman-York process with positive parameters, well, they tend to not have that property. People like to use the Pitman-York process because it has many clusters in the posterior. The proof shows that having many clusters in the posterior induces. So it does tell us that certain things that people like to do in practice actually do towards performance. And because the asymptotics kick in rather quickly, it tells us that maybe we should not be using the Pitman-York, but we should be instead using the Dirichlet process because the asymptotics kick in with like a small number of points anyway, and they don't have this bias, while the Pitman-York process still has this bias. But not bias in the sense that it's inconsistent, but bias on the straight end level. So that's those things. And for that parametric part of the parameter, that's just easy. There's like whatever sensible prior. So if you want to inform us what kind of like non-informative prior you should be using, because there's a lot of people being quite convinced that the Pitman-York process has a lot of nice properties, and they give arguments why you should be using it, but it turns out that these properties actually are, at least from a frequentist point of view, so So that's still quite, like you could try that, but it's still difficult because like with a positive parameter, you immediately have a polynomial in terms of clusters. Well, so if you have, let's say, draws from a fire. So you have one draws from a fire, you have some polynomial of answer n to the power with like sigma. No, like the number of clusters is n to the power sigma. So
play out this game. I have not done the computations, but like it is, I think, possible to do this. I mean, you just take something that goes exponentially fast to 0 and that should work. But like the Dirichlet process only has like a logarithmic number of clusters. So there's like a big gap that you need to overcome. Yeah.
Actually, if you want to mimic that version,
yeah. Yeah, you can, but like that's not what people do in practice.
because this is a bit sensitive parameter, so people have tried putting fire on sigma and then
Yeah. Yeah, but I've not tried what happens if you put a hyperparameter on the sigma. But which kinda can go wrong, and this is what, for example, if you use the Pitmanion for like distribution estimation, so not outside of this mixture model, is that this sigma converges to a positive value. But if you want to have the best estimation, sigma should be converging to 0, or ideally be 0. So that's sort of one of the things that can go wrong. But yeah, you can, of course, like play with that rate and try to get the like entire proof going through. That's definitely possible.